Hello everyone. So this is going to be the video on section 2.3, and this is on linear first order differential equation. So anytime you have something that is first order and linear, you can write it in this form, which is y prime plus p of x multiplied by y is equal to q of x. And you can solve it by using what we call the integrating factor. So the integrating factor method requires us to figure out this u of x. And this is just from an observation that the left side is somewhat a result of the product rule. So if you notice the left side, you have a y and a y prime, and you usually get that as a result of applying the product rule. So if we examine what we would get if we take the product rule of y of x with another function, we'll call that guy u of x. And here I'm going to differentiate the product of these two functions with respect to x. Then by the product rule, you'll get u of x multiplied by y prime of x plus u prime of x multiplied by y of x. And here we're just going to write that as u times y prime plus u prime times y. Okay. So this is the result of the product rule applied to this product of u and y. And we want to somehow relate this with what we're seeing here on the left side. If this is indeed the result of a product rule, then what we need is something in front of this y prime. Right now, there's nothing. So what we need to do is kind of fill in that blank. So what's missing in front of that y prime? A u. So we're going to take this differential equation. We're going to multiply by u of x. And the whole point here is to try to figure out what this u of x should be. What is this integrating factor? Okay. So if I multiply the left side by u of x, I get u of x times y prime plus u of x times p of x times y is equal to u of x times q of x. Okay. So now we're going to compare these two again. If they are indeed the same thing, then here I have u, I have y prime, I have y, and here by process of elimination, I get that my u prime should be this u of x times p of x. So that's another clue on what this u of x should be. U of x should be a function such that if I differentiate u, I get u times p of x. Okay. And this turns out to be a separable differential equation because u prime is du dx. Here I have u, I have a function in terms of x. I can separate the dx from the du, move the u over by dividing by u, move the dx over, and once it's separated, we can now integrate the left side with respect to u, integrate the right side with respect to u, and integrating the left side with respect to u will give us natural log absolute value of u, and the right side is simply just this because we don't really know what p of x is. And so what should u be? U is e to the integral of p of x dx. So here we found what u should be. And why would this be useful? Well, if we know what u is, then we can now take this differential equation with the u, and the left side is exactly the result of the product rule, where this is the u prime. So now I get to rewrite the left side as d dx of u times y. Okay, and the right side remain as is, u times q of x. And our goal here from the very beginning is to solve for y. And if you're differentiating this product with respect to x, in order to cancel out this differentiation, we're going to integrate. So I'm going to integrate the left side, take the antiderivative. I'm going to integrate the right side as well, both with respect to x. So dx, dx, and that will cancel the d dx. And the left side is just u times y, and the right side is simply the integral of u times q of x dx. And we are one step away from getting the answer of what y should be. And y is going to be 1 over u of x times the integral of u of x q of x dx. And u is this integrating factor. Okay? So this method just comes from the observation that the left side of this linear first order is somewhat a result of the product rule, and we're missing that integrating factor, u of x, that would make it really the product rule. And from a few arguments here, we get that u should be of this form. And once we get u, which is the integrating factor, here's the answer. All right, so let's try one example. And so this is going to be number 15 in the book. And it's going to be x squared plus 1 dy dx plus xy minus x is equal to 0. Okay, so before we even start to figure out what this integrating factor is, I need to put it in this standard form. And that is, I need to get y prime by itself, and then that second term is going to be the y term equal to, and then the leftover would be in terms of just all x. So I'm going to rewrite this, but instead of writing dy dx, I'll use y prime. All right, so there it is. This is my y prime term, this is my y term, and this is the x. So I'm going to move it over to the right side, which will become a positive x. And here's x squared plus 1, y prime, and this is xy. It is still not in standard form because I want that y prime by itself. Right now it's being multiplied by this x squared plus 1. So what we'll do next is divide everything on the left and right side by x squared plus 1. So that's going to give me y prime. And for the y term, it's going to be y multiplied with this x divided by x squared plus 1. And on the right side, now it's going to be x divided by x squared plus 1 as well. Okay. So now that it's in standard form, I'm going to identify this as my p of x, this guy as my q of x, and we're just going to apply the formula of the integrating factor, where u of x is going to be equal to e to the integral of p of x, which is x divided by x squared plus 1 dx. All right, and what is the antiderivative of x squared, x over x squared plus 1? Well, there's a chain rule here. If I do a u sub for the bottom, I get du on top. So you can easily see that there's a relation between the bottom and the top. The top is the derivative of the bottom, except there's a x over 1/2. So this should give me the natural log u of x is equal to e to the natural log of x squared plus 1. But here I'm missing a 1/2 in front. Now, yes, there is a plus c, but it's a very useless c. I'll show you guys how it's a very useless c, because in the end, it will just cancel out. So if you consider a c, which you don't have to, but for this example, I will, that will give us a constant in front. So e to the c is going to give me an a in front. Okay. And let me clean this up a little bit further. You have e to the natural log, which will cancel out. So let me rewrite this as e to the natural log of x squared plus 1, and that whole thing is to the power of 1/2. So my u of x here is going to be, you're going to cancel this out, and you have this x squared plus 1 to the 1/2. Now I am doing a lot of things where I'm just ignoring all these absolute value. Really at the very beginning here, this u of x is not by itself. There should be an absolute value right here, and we really just ignore that. So in this case, we can just ignore it, because this a in front will just absorb all that plus or minus. And as I said, this a is just a very useless a. So as it absorbs all the plus or minus from the absolute value, you'll get to just cancel it out. So you don't have to worry about it. So here, this u of x is equal to the square root of x squared plus 1 with an a in front. And that is going to be my integrating factor. So what is my solution? It's going to be 1 over u of x, the integral of u of x times q of x dx. So that's going to be a square root of x squared plus 1. And here's a square root of x squared plus 1. And you see how this a will just come out in front, and it'll just cancel out with that a. So in the end, you can just ignore that a. Okay? And what is my q of x? It's going to be x divided by x squared plus 1 dx. So my solution will look something like this. And I have to take the integral of, so that's really x squared plus 1 to the power of 1. And that's really x squared plus 1 to the power of 1/2. So after you cancel 1/2 away, you get square root of x squared plus 1 in the bottom. So we're very close to the answer. All I have to do now is take the antiderivative of this function, and we just need to apply the u sub. So u is x squared plus 1, du is 2x dx. But I just see an x dx, so what happens to that 2? You bring it to the left side, and you get 1/2 du is x dx. So this blue part is going to be equal to the integral of du 1/2 divided by square root of u, or that's really 1/2 u to the negative 1/2 du. And so power rule tells me to add 1 to the power, divide by the new power. Well, that's the same thing as multiplying by 2, but I already have a 1/2 in front, so that's going to cancel. So this is really just u to the 1/2. and there's a plus c, of course. But what is u? U is x squared plus 1. Okay, but that's not the answer. This here would replace this blue box. And so my final answer will be 1 over square root of x squared plus 1 multiplied by square root of x squared plus 1 plus c. Okay. And so the final answer will simply be, when you multiply this together, that's going to be a 1. And you have a c divided by square root of x squared plus 1. And this is the solution to this differential equation. Okay, and that's it for section 2.3. See you guys in the next video.